I think we can start. If there's a few latecomers, they will join and catch up in the middle. Thanks again for attending to this new webinar. For those who don't already know me, I'm Guillaume De Calan, the CEO of NANOE'S, and today we're going to talk a bit about additive manufacturing of ceramic and metal parts by FDM. More specifically, we're going to focus today not really on the technology itself, but on designing for this process and kind of design rules we recommend to our customers. So before we really get into the subject itself, a few words about NANOE, about who we are and what is exactly our role in 3D printing. NANOE, we are a raw material company. We're a medium company producing industrial scale raw materials for ceramic, mainly for traditional process, so not only for 3D printing, but also for more traditional process. We focus mainly on ceramic materials, even though you will find out that we also do a bit of metal, and in ceramic, mainly on a class of material which is called oxides, where you will find alumina, zirconia, and a few other ones. We're still a relatively young company. The company was created 12 years ago. So we still have a very strong focus on additive manufacturing, on innovation, and additive manufacturing is really the new development at NANOE. What do our customers do with our materials? Well, they make ceramic materials, ceramic parts, and it is done mainly by traditional process like pressing and injection molding, which is very well known in the industry. And more recently, we've also launched a line of materials for 3D printing, and we'll go more in details about this line of product. But it's important for us to explain that even in additive manufacturing, we are in the same position where we are mainly a raw material supplier. This is what we do. And of course, all of these processes are only shaping methods afterwards. In order to have a dense ceramic or a dense metal part, you need to go through a sintering phase, which is a heat treatment at very high temperature. Main applications of our product goes in aerospace, medical, semiconductors. That's really some of the big applications. Quite a few wear parts, some application in fluid handling and chemistry, and a few aesthetical applications with ceramic parts for watchmaking and for jewelry. When we talk about additive manufacturing, we'll find out that we actually have a broader range of applications, but these are really the main ones, especially for the traditional business. Now, about what we do in additive manufacturing. So as I told you before, NANOE is a raw material company, and it's really important for you to understand that this is where we come from. This is our DNA, which means that when we started additive manufacturing of ceramic, we wanted to develop raw materials adapted to the technology on the market, which is quite different from what I would say more traditional players are doing, where they will adapt, they will design a printer for ceramic. We did the reverse way. We designed our materials to fit on standard printers from the market. So what do we do at NANOE? Basically, it's very simple. We make feedstocks of powder plus thermoplastic binder. That's really the core competence, mixing powders with different type of thermoplastic binders. This is where most of the IP is. We have a few patents, and they are mainly focused on the formulation. Then we extrude this filament, which is also something which requires some know-how to get filaments out of a few materials. Ceramic first, alumina and zirconia, which are really our main materials, and also some metals with 316L stainless steel, and a new steel which is coming out right now, which is a tool steel. the process itself afterwards, once we've done this filament, what do we do with it? Well, it's starting to be something which is pretty well known. It's a three-step process. We first will print the filament on a standard FDM printer. Again, we don't manufacture the printer, we just buy normal printers from the market and put our filaments on it. And once you have printed the part, you need to remove the binder and to sinter it to get to a dense material, which is done in two steps. First, chemical debinding, and then the parts are put into a furnace where we will burn the rest of the binder and sinter the part. So this is what is really remarkable in our case about this process is that, again, we are not using any specific equipment. We are using FDM printers, which are usually intended at printing thermoplastic filaments, and we are using standard sintering furnaces from the market. Of course, before that, you have some file preparation, and afterward, you have potentially some post-processing. I won't go too much into details about the process because we did quite a few webinars about this already. Of course, if you have some questions, I'll be happy to discuss them afterwards. But today, really, we want to focus on, let's say, what can we do, what can't we do with this technology? We feel it's extremely important when designing a part to know what should be done to make it compatible with the process. Just to precise this, because we have a lot of questions about this, to make it really clear. So NANOE, again, we are a raw material supplier. So the core of our offer is the raw materials, filaments of zirconia, alumina, and stainless steel. But we do offer also a package of machines which allows to use our materials, which include printer, debinding kit, and sintering furnace. This is really in the spirit of helping our customers to learn the technology and to start. Of course, none of this is compulsory. Some customers are already equipped with printers, with furnace, sometimes with both of them. And in that case, they can directly purchase the filament and start printing ceramic and metal. Before we go really to the design guide, which is the core of this webinar today, just wanted to finish with this. What are the main interests of this technology? If you really go deep into comparing it with different technologies, what do we bring which is different from other technologies? Well, we feel there's two main features that are really strong point for this technology. The first one is this is a very easy to use technology, very easy to use system. FDM is really a very simple technology. You can learn to print such parts with such technology in a very quick way. It's very robust, and we usually count a training of 1 day to get started with customers. I should add that it can be used by really any trained technician and with very little health and security issues. You don't have any volatile powders, you don't have any toxic materials, which really makes it more simple to use. The second strong point for the technology is it's a low-cost investment. When we talk about additive manufacturing of ceramics and metals, we usually talk hundreds of thousands of euros or more to get a system in-house. And this is a huge step to take. Sometimes you don't already have a production use case for this. You just have a few parts you would like to make, or some toolings, or some parts that would justify a smaller investment, but which are not compatible with three-digit investment. The big interest of our technology is that we use standard machines from the market, which makes it much more affordable. And the package we offer for printing ceramic and metal parts starts at 10,000 euros. You have no equivalent on the market, nothing that allows you to print ceramic and metal part at those costs. And finally, two other strong points are the versatility of this platform. It's one of the only platforms where you can print both ceramic and metal. And of course, we plan to add some new materials in the future on top of those already available. And it has a relatively good accuracy. So it's not the best on the market, clearly. If you compare with SLA for ceramic, for instance, SLA is more precise. But we still found out that most customers have a prejudice against FDM and think this is not a technology precise enough for our application. And actually, accuracy can be relatively good on parts printed roughly up to 100 millimeter. After sintering, they'll go down to 80 millimeter. We still have accuracies in the range of plus minus 0.1 millimeter, which is, considering the technology and the kind of materials we're talking about, relatively good. It also obviously has the possibility to print a lot of internal features, close porosities, hollow structures, any kind of internal feature. That's really a technology which is well adapted to that. That's it for the short presentation of the technology. Now we'll go to the design and printing guide. Our recommendations when you start using this technology. And really, these recommendations should start with design. We usually have a lot of questions from our customers about how do I print this part, but not a lot about how should I design it. And this is clearly a mistake. If you don't design the part with the process in mind, you're probably losing something. That doesn't mean you won't be able to print your part, but you're probably not taking the full interest of the technology. And that's obviously a shame. There's three parts in this. The first one is talking about the advantage of this technology. And this advantage should be, as much as possible, included in your designs. You should take profit of the advantages. Then there's a few design rules for FDM of ceramics and metal, and we'll go through them together. It may not be completely exhaustive, but we will talk about the main ones, which are more, let's say, recommendations, and a few printing recommendations. Again, we can't cover all of the printing recommendations we give to our customers. This is a one-day training and not a one-hour webinar. Let's start with 3D printing advantage. When we design parts with 3D printing, we should have in mind the advantage of the technology. Well, the first one, obviously, is that we can print with ceramic and metal. So we should choose the best material for each application, of course. And that's really important. And that will also have an impact on your design. If you print with metal or ceramics, probably your designs can be quite different. The second thing is we have access with this technology to very complex structures that you could not manufacture in any other way. Articulated parts, internal features, high level of complexity, all of this is made possible with the technology. So as much as possible, you should take profit of it. Of course, the last one is that, especially for small series, medium-sized production, it's also a question of time and money savings. You can be faster in getting the part, and you can try to make it cheaper. I won't go too much into details about this one because this doesn't have a big impact on design. It's just one of the reasons why customers will use our system. So let's go a bit to these advantages in terms of design. The first one is that you can very easily create relatively complex patterns. Here, this is a typical example of a very well-known kind of pattern, which is gyroid patterns, which are extremely complex, if not impossible, to manufacture by traditional process. A few examples of how can that be used. We had some very nice use case with one of our customers, with maybe in the webinar, Avignon Ceramic, who's manufacturing materials for foundry and for the casting industry. They needed high temperature resistant filters for the foundry for filtering molten metal. And they were interested in the possibility to print very complex patterns. Typically, the filters you saw in the previous pictures, they cannot be produced by regular process. It's just not possible. With our system, you can print it in many different ways. Here, the first examples we made were actually produced just by using the infill possibilities of the slicer, but you can also use a lot of softwares which are dedicated to designing any kind of complex structures. Again, it gives you access to structures that would just not be possible by traditional process. Here you have it. Again, this is a dual-read one. Unfortunately, we can't show everything, so we keep a bit the same pictures. The idea was really to make a highly tortuous lattice with a non-brittle structure, and that's really important. We wanted to have small features, high tortuosity, but we still wanted the part to be non-brittle and to avoid very thin structures at some point that could break during pouring the molten metal. And so that's, again, the big interest of this technology here. Of course, you can also adapt the outside shape, so you can do both together. You can put some complexity inside and also adapt the outside shape. Typically, make a cone for the molten metal to flow in, that kind of things. A second design advantage that you can take profit of is the possibility to print articulated parts. And this is particularly interesting with ceramic, a bit more than with metal. Why? Because usually making articulated parts in ceramic is almost impossible. Typically here you have a bracelet. Making that kind of part in ceramic is just impossible by traditional process because we don't know how to weld ceramic. We can't weld ceramic and we can't bend them. A few examples of articulated parts. So we had a few ones for aesthetical applications. So customers in jewelry and watchmaking who wanted to make, well, tailor-made sized, customized products where you could add any kind of features, but they also were interested in producing articulated designs. And I'm especially thinking about the parts you saw just before. Here you can see this one is not a full part, but just to show the interest of it, making that kind of chainmail in ceramic with any traditional process is completely impossible. So that's something which opens new designs, and you should try to benefit from this in your designs. The third big advantage of the technology is the possibility to print internal features. These internal features can be hollowed out or channels or anything, and that's really a great advantage of additive manufacturing. And again, if you can take some benefit from it, that's really interesting. Same customer again, Avignon Ceramic was requested by some customers to print what we call flow sensors or pitot probe, but which needed to resist to very high temperature, which explains why it was made in ceramic. And this is typically parts that are completely impossible to manufacture by traditional process. You have an example here of another part in the same principle, which is a pitot probe. How does that work? You have some channels on the front, which will measure first pressure. You have some channels on the side, which will measure second pressure. And the difference between what we call dynamic and static pressure will give you the speed of the flow coming through this probe. The part really does not look impressive. It's a small part. It's quite simple to make by additive manufacturing. But if you want to do this by any other process, any other ceramic process, it is just impossible because you have these internal channels with several changing directions, which make it impossible to machine. impossible to inject or impossible to mold in any other way. Of course, once you're there, you can play a bit with the technology. You could add a cooling or heating circuit on top of this. You could have add some other features also. And just to finish on this application, why did they want it in ceramic? Again, it's because ceramic allowed them to use the part up to more than 1600 degrees Celsius. Another example of these internal features would be to make some quite complex designs for pump parts or for parts manipulating some fluids, and these designs would not be possible to make with injection molding or pressing or whatever. Again, we needed ceramic in this application. Typically, this kind of part, this is a pump shaft. You have a lot of holes everywhere. You have some internal channels, and the feature itself are quite complex. Making this part in a traditional way would be extremely difficult to do. It could be made in both ceramic, depending on the application itself. So that's it for our first recommendation. So our first recommendation is really, when designing a part for additive manufacturing, you should keep in mind what is possible. And a lot of things that you thought impossible are suddenly becoming easy to manufacture with the technology. Any kind of internal features, any kind of articulated part, any kind of complex design in general should really be something you keep in mind. Well, let's go to design guidelines. Just a few words about these before we start. Here we have collected a few design rules that we found out by printing a lot of parts. These are more recommendations than really rules. You'll see some minimum feature size, some maximum size. We have already been below the minimum size, on top of the bigger size. It's just that when you get outside of these figures we will give you, you get to something more experimental, and you can't be sure before you print and you sinter the part that the result will be good. These design guidelines are here to help you design parts that will come out of the printer good on the first trial. That's really the idea. So the first thing is quite simple, the size. We keep being asked a lot, what's the smallest size you can print? What's the biggest size you can print? Again, as I told you, these are general guidelines. You can print smaller, you can print bigger, but it's just more complex and more difficult to do. We usually recommend to have parts which are relatively big. It's not made for micro manufacturing. So typically a part that will roughly fit in a box of 7 millimeter would be nice, or 1 centimeter is really a nice dimension for us. If it's much smaller than that, not saying it's impossible, it's just more difficult. You will probably need to use smaller nozzles, and the printing process will be a bit more complex to get used to. On the maximum size, this is more linked to the size of our furnace, actually. The furnace we offer will not allow you to make parts bigger than 200 millimeter per 70 per, let's say 50, 55, and up to 70 in the middle. If you have a bigger furnace, you can probably make a bit bigger. We still recommend usually to stay in the box of 100 square of 100 millimeter. Again, it's perfectly possible to go above that, but this makes it the process more complex. Second very important rule is wall thickness. There's a minimum and there's a maximum, and the maximum is even more important than the minimum. Maximum dense wall thickness is linked to debinding, so it's really a physical limit. On top of a certain level, we will not manage to remove all of the binder without causing any deformation or any cracks. So we usually recommend our customers to stay below 5 millimeter. Of course, it's not always possible. A lot of customers want to print parts much, much bigger than that, which is not a problem. We just we are just talking here about dense wall, which means if you have a wall which is 1 or 2 centimeters thick, we can print it very easily, but we will probably recommend you to have a shell which is dense of a few millimeters, and the rest of the wall will be filled with what we call an infill with a specific pattern, which would be again gyroid or honeycomb, but it will not be 100% dense. And this rule of 5 millimeter really helps getting some good results on the first trial. So you should really follow these. In terms of minimum wall thickness, it's a bit harder to give a figure because we've been printing very small walls in some cases. But if you are talking about a freestanding wall alone with no supports, just by itself, we usually recommend to print it with a minimum thickness of 1.5 millimeter. Again, I'm talking here about a freestanding wall with no supports. But the features that we can add, what is the minimum feature size that we could do? So we can do very small, very intricate sizes, very intricate designs, very intricate features, but still, if you really want the details to come out fine, you need to be careful. If you want to make holes, typically, if you want your holes to be very clean, to be completely spherical, well, you should stay on top of 2 millimeters. If it's less than 2 millimeters, you'll print it, of course. You'll have a hole, but will it be nice and spherical? That's another question. In terms of pins, it's a bit more difficult even because the pin needs to hold by itself. So we usually recommend to stay on top of 3 millimeters. What about other features if we want to, say, put some writings on the parts? What size should they be? Well, we usually recommend for embossed and debossed features, it's almost the same values, not exactly, but almost the same values. We recommend to have a minimum size, which is not the same if your feature is on the top of the part because you print it on the Z direction, which is easier, or if it's on the side of the part where it will be slightly different. If it's on the top of the part, the width of the features should be 8 millimeters. It does depend on actually on the nozzle size you're using. We say 8 millimeters because that means 2 nozzles. If you have a smaller nozzle, you may do smaller details on your part. And the height of it, so that you can actually see it and so that it doesn't break away at some point, should be almost 0.5 millimeter. If it's on the side, well, it needs to be a bit bigger. When we say height, you need to be careful because since it's on the side, it's actually what we call width in the previous version, which is the section of this, and it should be a bit longer so that the print is clean, and the depth again should be something like 0.5 millimeters, so very similar. You have the same values for debossed. It's really very close in terms of details you can print. You can print a bit finer details with a debossed feature, but that's really marginal. Then there's the question of overhangs. FDM is a process where you print layer by layer, of course, and you can't print on top of nothing. You need to have materials below it. And if you have too much overhang, you will need supports. The maximum unsupported overhang is 40, 45 degrees, depending a bit on how fast you're printing. But let's say 40 degrees. This is really important because as much as possible, you should try to design parts that does not need any supports. That's really a significant advantage if you can avoid supports. And having that figure in mind will help with that. To know exactly how you design your part, you need to know what kind of angle you can print without supports. And finally, something quite important, it's not absolutely necessary. If you don't have that, you can always print a lot of support. But we really recommend to try to allow for a flat surface somewhere on your part. And ideally, this flat surface should be at least 2 millimeters inside. Of course, this is to put on the plate, so that this is where the print will start. Again, it can be done otherwise if you don't have this, but this will really help your print. So sometimes it's not much of a change in terms of design to allow for a flat surface somewhere, and it will help printing so much that this is really worth modifying a bit the design. Here we are. A few words about designing, printing guidelines. So I'm not going to go into details here because we do send to our customers when they buy the system and when they buy, when they buy the filaments, we do send detailed printing guidelines. We send printing profiles that can put directly in the slicer. So I'm not going to go into all the details of that, and we've already done some webinars also on this part. So I'm just going to fly around a few very important aspects that maybe are not covered precisely in this previous webinar. So the first one, of course, we've already talked about this a lot, but is about shrinkage. When you do the full process, you print a part and then you sinter it afterwards, which means you'll have a shrinkage, roughly 20%. That means that if you want a part of a certain size, you actually need to print it bigger. So with our guidelines, we give what we call oversizing factors that you need to apply to your part, which can be done either during design or afterwards just in the slicer, in the software that will prepare the print. Just to explain where that shrinkage comes from, it's quite natural. You have a densification of the part. You start from a part that has something like 50 to 60% density once you have removed the binder, and you go up to a part that has between 90 and 99% density. And that obviously means you need, well, the air needs to go somewhere, the porosities, they need to go somewhere. And so you have some material diffusion and some shrinkage of the part. On this part on shrinkage here, it's a picture where you see the part at the different steps. Printing on the left, I think it's sintered in the center and sintered and polished in the end. You can see the difference in size, which is quite significant. Roughly 21.5% for zirconia, 20% for white zirconia. So if be careful when we say 21.5, that means on the part of 100 millimeter, you will go down of 21.5. So that means when you do it the reverse way, if you want a part that makes 100 millimeter, you need to multiply the size of your part by 126.6 for black and 125.4 for white. And the other materials also have their specific shrinkage, of course. Really not something to forget. If you forget it, you'll find at the end, once you've sintered the part, that it's too small. Well, it sometimes happens, and this is really a loss of time. Another general advice that should seem obvious, but it does depend on technology, so it's important to say. In our case, for FDM, we really will be looking for having as much as possible contact with the printing bed. There's two reasons for that. It will increase the adhesion to the bed, so it will increase the quality of the print, and it also will reduce the printing time and reduce the amount of support you need. This is really something important to think about the orientation of your part. Here, of course, the part is obvious. You will have parts where it's not completely obvious because it's a compromise between having a surface, good adhesion between the plate and your part, but you also want to accommodate for some specific design features. You want to avoid supports. All of this will make choosing the orientation of your part a challenge. A few other guidelines. if you have a wall with a very high height to length ratio, you should consider printing it on a stand. If not, you may have problems doing printing. We also really advise to avoid any abrupt change of size and any square angles. Both of these because this will lead to deformation or cracks during debinding and sintering. Really, as much as possible, you should avoid any square angles. This will create defects, which will be the initiation of crack propagation if there is any cracks. And of course, as much as possible, if you can reinforce thin walls, that will help, because if not, you may have some deformation. And if you're printing metal, especially, you may have even sagging of the part during sintering. So when the design allows for it, you should try to reinforce it. A little something about printing thin walls. So this is a part that was asked by a customer. It's really a simple part, you know, a wall. And he wanted it to be printed in XYZ just to compare the mechanical strengths. And we found out that this actually is a very difficult part to make. Why? Because so you're going to accumulate your layers, but you do have some kind of stress, which is here during printing. You don't see it during printing. You have a very nice wall, very straight, but after sintering, this stress is going to really pose some big problem. So what we do is, instead of printing each layer in the same side, we will change side in each layer. This allows to avoid any stress or to compensate for stress in the part and to avoid deformation. Nice animation, and here is a picture of the part, which usually is really what makes it clearer. This really is something that will happen during sintering, so you don't see it when you print. You're just perfectly happy with your part, but after sintering, you see some huge deformation in your part. So that's why trying to mitigate for this is important. There's a few ways to do that. But again, if we can avoid thin walls, it's going to solve the problem. If you can print alternating layers, it's great, but not every slicer allows it. So it's a challenge to find the parameters that allow this. There's a few others way to solve the problem. But anyway, that's something you should keep in mind. Thin walls are complex to print, and especially complex to sinter and to keep really straight. That's it. So this webinar is almost over. I'll answer to your question, of course. What I really wanted to stress on is these design guides we're giving you. It's not really a limit of the technology. You could probably print smaller, you could print bigger. You can do a lot of things with the technology. But this is a guideline that allows you to be confident about your success rate. If you follow those guidelines, the parts you're going to take out of the furnace are going to be good almost 100% of the case. If you stray outside of these because you really want some fine features, you really want a very big part, up to you. It's really interesting. You may yield great results, but it will probably need some more trial and errors before you actually get to the right part. Well, I'm done for today. I'm going to try to answer to your questions. Of course, you can still follow us on LinkedIn, which is where you'll see most of our news. You will hear about our next webinars. We try to keep it rolling. So if you have any topic you would like us to cover, you can, of course, ask for it in the Q&R, and we'll try to cover it in the next webinar. And you can also go on our website, nanoe.com, which is really about our traditional activity, and Zetamix, which is about our 3D printing activity. I can see that a few participants has asked to speak, so I'm going to open your microphone. Jonathan was raising hand. So go ahead, Jonathan, if you have a question. You can now activate your microphone and ask it directly. No, he's not there anymore.
Hello.
Hello.
I have a question about at first, thank you for your presentation. And I have a question about the gyroid. What's the size of the part that you was able to print? And what's the dimension of your porosity? And how did you design this gyroid?
In the case of the part you see here, to answer to the design first, it was it's a bit of a it's cheated a bit because it's not really designed. We used the slicer to make them. So in the slicer you have access to that kind of parameters. So we started with this, which is a block of material, and with the slicer we instructed him to make the infill. In terms of size, well, we could, that's the interest, we could adapt the mesh size. Here you see a few different ones with different kind of sizes. The block itself must measure something like 6 or 7 centimeters. But we did mesh down to something like 0.4 millimeter up to a few centimeters up to a few millimeters, sorry, in hole size, depending on the parameters. Of course, for the real application, you need to design the cells. It's just that we don't have access to the pictures of the real parts. But if you want to go to the real application, you want to design the cells, and there's a few software tools available for that. Here, the idea was just to show the possibility.
Okay, and can you give me, for example, some softwares name that I can use for designing?
Well, I just had a discussion recently with Jane 3D, for instance. They've just sent me some amazing structures that we want to try and print. So that's an example, but I'm sure there's quite a few ones. I'm not an expert here. You need to remind that we're material manufacturer, so we really try to help our customer on this, and talking about design guide for us is in that spirit, but in the end we're really not, it's not our job to design parts. Okay, we feel that that's really where the value of our customer is, to take that technology and to develop new products thanks to that technology. That's where our customer brings something really remarkable.
Okay, thank you.
I saw a few other raised hands. I'm going to try to activate those. And there were a few written questions also. If you want to ask a question directly, you can just raise your hand, and I'll open your microphone. If not, I can also try to answer directly. So there's Eric who had another question. Eric, you should be able to turn on your microphone.
Yes, do you hear me?
Yeah.
A question about post-processing. I don't know if you're able to answer. One of your examples was quite interesting with a glossy part, a chest part. How did you get this kind of surface? What kind of post-processing have you done on this kind of parts? Or that's it.
Where is it? I can't find the part anyway. I think people will have seen it.
It was quite at the end, I guess. It was not
anyway,
at the beginning.
So about polishing, that's one of the interesting things. Both with ceramics and metal, you have material that polish really well. They have enough strength to be polished in industrial process, and typically the process we used here is what we call tribo finishing, or tumbling, if you want. Basically, where you'll put the part in a rotary tumble with some abrasive materials, and you just let it stay in that media for quite some time, and this will polish your part to very nice level of surface finish. Of course, the defect of this is that you do polish all of the parts, so you can't keep any very sharp angle if you do triple finishing. But apart from that, this really works well with both ceramic and metal.
Okay, thank you.
So I will just go and look if some other raised hand. No, so we'll just go to the Q&R. The first question from Stefan was, do you modify the printer? So really our philosophy is to try to be adapted to printers from the market, so as little as possible. In our case, when customers buy the printer from us, we use printers from a brand which is quite well known, which is Brace 3D. It's not the only printer compatible, but it's one that we know very well. And in this case, we almost modify nothing except the spool holder, because we need the filament to be really as much as possible directly on top of the extruder, because the filament is quite brittle. So that's the only significant modification we do to the printer. Apart from that, really our philosophy is to be compatible with standard printers, as much printers on the market. So yeah, the idea is to avoid modifications. Shrinkage doesn't change for X, Y, Z. So there's no simple answer to that. Hello, Federica, by the way. For ceramics, we usually consider that if there is a change, it is very small. It's not a very significant amount of change. If you do very big parts, you may check, but we usually give one oversizing factor, and that's it. For metal, it's different. For metal, there's a different shrinkage in X, Y, and Z. And we give two different shrinkage in that case. So which slicer allow you to change the orientation clockwise versus counterclockwise? So, that's an excellent question. For the moment, almost none. I think there's an option in a slicer called Slicer. And we've also been experimenting with Grasshopper, which works with Rhino, which is not really a slicer, but which is a programming language. We're a bit working on that. For the moment, we try to turn around the problem in a different way by avoiding very thin walls, or if they're very thin, by printing them in a single pass. But there's a few slicers offering, let's say, experimental version of this clockwise versus counterclockwise, and we're trying to push the developers of this slicer into making it more accessible. You mentioned compatibility with standard FDM printer. Is there a list of printer and furnaces sintering profiles which has been tested and certified for your materials? So for the furnace and sintering profiles, that's very simple. We give sintering profiles. So if your furnace can follow it, it should be compatible. I should add that if you want to make metal parts, you need it to be compatible with neutral gas. So you need to have the possibility to put it in pure argon or hydrogenated argon. Now, about printers, we do have a few printers that we have tested and validated with our filaments. It's not exhaustive. What I can tell you is it's very rare that we can't print with a printer. What we find out that some printers will offer us a better reliability, more success in print, less risk of breaking the filament, which is really what can happen since the filament is relatively fragile. So we have a few ideas about printers which are very favorable for that, a few brands, and also some general guidelines. We prefer direct drive printers, and we prefer printers which has, let's say, a good configuration in terms of extruder. We particularly like extruders of a brand which is called Bondtech. If you have a printer which is direct drive equipped with Bondtech, you can be absolutely certain it will work. Another good question. How does the mechanical strength of ceramic parts compare with those produced with traditional process? Well, we are still working on that. In assessing mechanical strengths, it's a complex question because it requires a lot of tests. Mechanical strength will depend a lot on printing parameters. So you need to check those parameters before giving any precise value. For the moment, the result we should publish some paper by the end of this year about zirconia. That's the first material we tested in details. The first results we have give us two things. The average value mechanical strength is quite good. It's comparable to bulk material, a bit below, but something like 10-15% below the bulk material. But you do have a difference between X, Y, and Z is less strong. I don't have the precise figure, but again, we're going to publish some paper soon, so you can find this in the paper soon enough. So what about post-process? Well, post-process, I didn't insist a lot about the process itself because, again, we did some webinars about this in the past, so I didn't want to take too much time on the process. But still here you can see the full processing route. The first thing is printing the part, of course, and then in terms of post-process, we usually have two steps: a chemical debinding. You take the part and you dip it in acetone, which will remove something like half of the binder, and then the part is put in the oven, where you will first do what we call the thermal debinding, so burn the rest of the binder, and just after it, in the same furnace, you will go up in temperature and do sintering, which will densify the part. And lastly, once you have the part out of the furnace, depending on what you want, you may want to do some surface finishing. For metal, we do a lot of sandblasting, which really works great, or grid blasting anyway. For ceramics, what we've experimented a lot with is tunneling, which tribo finishing, which really works well. So when you are discussing about minimum feature size, are you talking about printed or tilted? So that's an excellent question. To be honest, I'm not completely sure of it myself. I'm not the guy printing. I would say it's probably printed, especially some features where typically a certain number of nozzle size. So I would say printed. So you do have that shrinkage of 20% afterwards. Is multi-material printing possible with this technology? So possible, yes. Is it easy to do? That's another story. So why is it possible to print multi-materials? Well, quite simply, we have a printer which has two nozzles. So that means we can put two filaments in it. We could even use printers which have more than two nozzles. There's a few ones on the market. You also have printers where you will print multi-material with one nozzle, but just by putting out the filament and putting another one afterwards. So it's possible. The big issue will be sintering. So it's easy to print. For instance, we could print a part in ceramic and a part in metal, which would be really nice in terms of, for instance, electrical properties. You would have an insulating part and a conductive part. So that has some obvious application and interest. So you can print it, no problem. But then goes to sintering, and managing to sinter two materials together is a complex bit of science. So for the moment, we kind of stay away from that. So there's a few labs who are equipped with our system and who are playing a bit with this. But ourselves, we just say, well, you can try. The possibility exists, but the real challenge will be about sintering. What are the quantitative differences in mechanical properties between X, Y, and Z? I'm sorry, I don't have the answer. I just don't know it by head. So I have in mind, so we were working with zirconia. Zirconia usually have a bending strength around 900 megapascal. The best printed part we had were around 700 to 800 in XY. And in Z, I might be saying something stupid, but I have something in mind around 600 megapascal. So you really have a significant difference with X and Y. So are the technical materials compatible with the use of soluble support materials? Yes, we've been using a bit of soluble materials. You can even use any thermoplastic, even if it's not soluble, because with the post-process, you're going to remove it without having to remove it by hand. If you heat up, it's basically going to melt at some point. So yes, we've done it a lot with PLA actually, and so we just heat it up to melt it away. It does work for some parts if you have some very fine details that needs to be supported, especially when it's piece-to-piece supports. If it's plate-to-piece, it's easier, but piece-to-piece support, sometimes we use the same material. And there's another question, which is, do you need the support for sintering? You don't need it for ceramic, but you do need it for metal. If you don't have any supports for sintering metal, you have a risk of deformation. If possible, I appreciate to receive recording of the webinar, so it's completely possible. You really need to fill in the form that was sent, which was on the LinkedIn page. If you do that, you will receive an email with the presentation slides, and if you request it, you'll also receive a recording, of course. Concerning filling strategies, is it possible to use any of those proposed on slicer, line, concentric, etc.? Is there any effect on final result? So we've played a bit with that. So far, we've never seen anything that was not compatible. It can have a bit of an effect on the final results. The first thing is some of these infills are completely anisotropic. That means if you may make honeycombs, for instance, the mechanical strength of the infill in X, Y, and Z is going to be very different. So that's something to keep in mind. Another thing is you may have, and here we're really talking on very fine tuning. If you do a big part, you may have a slight impact on shrinkage also. So that's why we kind of like gyroid, because it's almost the only infill pattern which is isotropic in 3 directions. You can see that someone raised hands. Jonathan, if you want to come in, you can. And just ask your questions. I'll keep answering those other questions. Are any other materials will be released in the future? So yes, that's really one of the key points of this technology. It allows for different materials. At the moment, as you know, we have 3 ceramics, alumina, zirconia, black and white, and 1 metal, which is stainless steel. We are releasing anytime soon a new steel material. It's not yet available, but it will be very soon, which is a tool steel. In the future, what do we have in mind? We should be releasing in 2021 silicon carbide, which is a very highly technical ceramics. And we do have requests for other materials, but for now, it's not very clear which one will come first. If you have an application where you really need the material, we are always interested to hear about it. do we have to sinter the piece in the same orientation that it has been printed? That's an interesting question. It's not absolutely necessary. It's usually recommended, especially if you have printed without any supports. That means that the part is self-supported. Well, it's better to sinter it in the same way. You may have sometimes good reason to do otherwise, but most of the case we print and sinter in the same way. Yes. Does removal of support potentially initiate cracks in ceramic after sintering? For those who know ceramic, potentially anything can initiate cracks. Ceramics are brittle materials, so during sintering, there's always this this question, which is not easy, about to avoid any cracks. We usually feel that if you're careful, you can remove support without any problem. But of course, you need to be careful not to make any shock on the part, or you will initiate some cracks. Again, if the supports are relatively simple, if all of them come from the plate, the alternative way is to do it either in a soluble material or even in PLA, and to use the process to remove it. But you don't remove it manually, and so you remove that risk. So is it possible to receive sample materials? So it's possible to purchase sample material. You can actually buy it directly from our website. We don't offer any free samples because we really have far too much request for it. But we do make small spools of 500 grams if you just want to try it out. Minimum layer size. We usually print layers of 0.1 millimeter. We do have customers who went down to 50 microns, but that's really the limit. In terms of nozzle, we have been done, especially with zirconia, which is a fine material, we have been done to 0.2 millimeter nozzle, so 200 microns. In which condition has the filament to be? It's better if it's dried. We send it in a vacuum sealed bag. Once it's open, you need to avoid humidity, because if you put some humidity in the material, it's going to become more brittle, so it's going to be harder to use. So there's a few questions from Brian. How many steps the binding process from green body to final ceramic? Physically, I would say 3 steps, but actually in terms of manipulations, there's only 2. The first manipulation is you take the part out of the printer and you put it in the acetone vase. That's it. You let it sit here for a certain time. We give recommendation for that. This will remove half of the binder. Second step is you take that part. Well, okay, 3 steps. You put it to dry somewhere. So you just drop it on some paper towel to let it dry. Once it's dried, which is quite fast, you put it on a plate and you put it on the furnace, and that's it. But in the furnace, there's 2 things happening. You have a first part of the cycle where you burn the binder, which is we call the thermal debinding, and then the second part of the cycle where you sinter the part. So that's where you get it dense. But all this is done in the same furnace. So practically speaking, there's mainly 2 steps: debinding, sintering. Do you observe any shape deviation of ceramic parts where compared to CAD model? Of course, that can happen. Ideally, not. But that can happen. Some simple stuff are sometimes difficult. Having a perfectly flat surface can be a challenge. It depends how it's printed, but it can be a challenge, to give a simple example. So you can have deviation. The idea for us is to try to keep it in a reasonable range where the part is acceptable as it is without any post-machining. Precision of plus minus 0.1, not micron, millimeter, I'm afraid. For object up to 80 millimeters, it's not any shape, any infill combination. What I can tell you here is if you're printing 100 millimeter and you want a 0.1 millimeter precision, depending on the complexity of the shape, but you may need to do at least one trial and error. So you print it, you measure it, and you find out that there's been a slight deformation in that direction, and you need to correct. And again, that question about slicer for clockwise, counterclockwise, well, I've already answered that one. There's a few solutions on the market, but nothing really satisfactory yet. I'm just going to check. I did saw some questions which were on the chat, so I need to.
It's in the car. Just cut the engine.
Hello.
Hello, bonjour. How are you?
Good. Do you have a question?
No, you've answered everything very well, thank you. I just need to look at the process of myself and sort of the process I have, and then really get in touch with you to sort of discuss which probably is the best way to proceed. Sort of but what was very interesting in the presentation was to really think the design of the product, sort of so that how it then translates into the 3D printing. So that was a really interesting point you made. Apart from that, no sort of current questions if at the moment. No, thanks.
Okay, thank you very much.
But no, it's a very interesting presentation, and the design side and the flexibility, sort of really interesting.
Thank you very much.
Yeah, it was like, right, okay, let's rethink the process of, like, obviously I've got a product that I was sort of thinking, oh, just 3D print that. And now you give me a real line of thought to sort of not redesign the product, but really think the product through before designing it, if that makes sense, or before putting in the 3D printer. So obviously that was really interesting. It's like, oh, yeah, okay, yeah, need to go back and think that process through first, and then sort of take it through then, yeah.
Mm-hmm. Well, yeah, really that's the idea, to try and help you think about the process from the designing part.
Yeah.
There is one last question from Marshall. Did you went to any issue of jamming the filament in the feeder, maybe because of not dry filament? So jamming can be an issue, not necessarily because of dry filament or not. It can be for a lot of reasons. We are using extremely highly loaded materials, which means jamming can happen. Really, with if you follow the guidelines in terms of printing, this is something extremely rare, but of course it can happen. All right. Well, if there's no any more questions, I think we have finished for today. I'll be really happy to answer any questions now or by email if you want to follow up on these discussions. And if you want to receive those slides and a recording of the webinar, you should try to register on the form or send us an email.